Good morning, everybody. Welcome to Lesson 7 of CE 5361. And there's 4 of you right now. And I'll talk slowly to give any other participants who are going to join us a chance to. The course content for Lesson 7, if you were to go to the Moodle site, I was just creating a couple of questions so that we'll log your attendance. It's not done yet, but it's one more question to go and it'll be done. So I'll get that completed by noon, I expect. The content is here at the usual place. Let me get my face pushed out over here to the right. That'll work. And under lesson materials, there's the PowerPoint section, which has the presentation slides that I'll go through shortly. There's a section in data called Green Amped Notes, and this is some older material. We recently uploaded, but the files are at least from 2014, maybe earlier, on some notes specific to a particular infiltration model. And I'll visit those today during the video lesson. And in these spreadsheets, there should be one spreadsheet that shows making the computations. At some point, I have in our script to do the same thing this spreadsheet does, but I haven't found it as of this recording. It's somewhere in my huge collection of files. Like y'all, I have thousands and thousands of files spread out over several different hard drives, so finding something old is not exactly easy. And anyone who's familiar with modern Apple products, and actually the PCs are the same way, the search engines are pretty terrible. They can find anything where they're going to benefit from getting money, but your own stuff is harder to find. Alright, that's my rant for the day. Video materials, what we do today will eventually be linked to this link. Right now it's coming up blank as it's supposed to. And in the reading sections, good, I got the readings up to date. Chow Mei Mit Maze, and then some other readings, and then here under old notes we'll take a look at that during the lesson today. Alright, with that, let's begin. So I'm going to work on a local copy to save download time. Oh, I guess I should check. Can everybody hear me? You're all muted. Let me fix that. There, now you're demuted.
I can hear you.
Okay, that's good enough for me. Very good. So here's the presentation part. So the topic is infiltration. So this is our other watershed scale loss process. So infiltration refers to the precipitation coming onto the watershed and a fraction of it soaking down into the ground. So the photograph is not infiltration. That's just a cool photograph of water here in the ponded environment going down into somewhere. If you're not familiar with it, that actually is a photograph of something called a glory hole spillway. And looking from the background, so I didn't take this photograph, that looks to be somewhere in the UK or in Northern California. And I know in Northern California I have a couple of glory hole spillways, and I've actually got to see them operational. It's pretty cool. It's just a big it's a large diameter riser pipe, and when the water gets deep enough, it goes over the lip, goes into the pipe, and comes out downstream somewhere. So if you're in a boat or if you're swimming around and you come across one of these, if you're swimming and you come across one, I would say do your best to swim the other way. But if you're already caught into the current, it's game over for you. You will not survive the trip down the spillway. If it's in a boat, you might have a better chance because the boat could get caught up on the edge of the spillway, and they could get a helicopter out to you and a news crew, and you'd make the evening news. Don't do that. So now we return to our usual diagram, and today we're going to look at the infiltration component. So that's the surface water soaking into the ground, and then by most definitions, infiltration is just the process of from surface into ground. And then what it does from there is it may migrate back out as runoff somewhere else or find its way into a lake. The second phase is once it's in the ground, it can get into the groundwater. That in this diagram, that's called percolation. Another common terminology for it is recharge. But relative to the surface water system, passing the air-soil interface into the soil would be infiltration in this context. The point being, infiltration is not always groundwater recharge. It's a component of it. The other point is that the slides are not advancing. There they are. Okay. So let's look at some definitions lifted from a couple of our textbooks and paraphrased. So infiltration is water that soaks into the ground. This water is often considered removed from the runoff process, and you will understand my qualification soon. It's the largest contribution to loss during a storm event. So in event-based hydrology, where we're interested in behavior of particular events, and by event, over a 3 or 4 day period, infiltration is by far the biggest loss component. It's certainly bigger than evapotranspiration by far, and if there's plant uptake, it has to infiltrate to get to the root zone anyway. So it's a fairly important mechanism. So most loss models in computational hydrology tools are often some form of infiltration accounting. And that infiltration accounting, as you could imagine, could be very elaborate or very simple. Historically, simple has been adequate for engineering applications. Elaborate is adequate for earth science applications. And then probably practical is somewhere between the two. So the diagram here, these explosion-looking things are, I'm pretty sure they're trying to represent raindrops hitting bare soil, and then it splashes back. So there's a portion here that's infiltrating, and then what's left is shown here as this red runoff arrow working its way to a stream or a lake. There's another component here called subsurface flow, and that's what I meant by usually the water's removed from the runoff process. So if there's infiltration here and a portion of the infiltrated water flows beneath the surface but above the water table and eventually reemerges in a surface water conduit, that is runoff, but it's a different type of runoff. Here in this diagram it's called subsurface flow, and I believe that's the usual terminology. And then there's a portion of the infiltration that can make it to the water table. At that moment, it's declared part of the groundwater system. Now, groundwater, too, can get to a surface water body and reemerge as runoff. The time frames of those are going to be vastly different. So, for instance, imagine a parcel of water hitting here in one of these three explosion-looking regions where the cursor is now circling around, hopefully making you nauseous. Let's see if there's any new people here yet. Nope, just us today, unless I made a mistake. And where was I? Okay, water comes here, a portion infiltrates, perhaps the travel time, so I'm going to invent numbers to try to convey an idea of time scale. Perhaps for surface water, the travel time from that point of impact to this water body is a few hours. As it infiltrates, the subsurface flow time might be on the order of a day or a couple of days, and the groundwater flow could maybe be a week. So that's the relative time scales. So the subsurface flow is fast enough that it could be considered part of the direct runoff hydrograph. Generally, the groundwater flow would be considered slow enough that it's more of the base flow or the long-term hydrograph behavior. That's not always going to be the case depending on the questions that we're asking, but it gives a conveyance of the relative time scales of the processes. So the subsurface flow and runoff are close enough in time scale that they can be gathered together as net runoff, and the groundwater flow is a longer time scale that usually it's just built into the base flow component. This is a diagram of a soil moisture profile, the left diagram. And infiltration is defined or governed by soil properties and the ground cover. By soil properties, what type of soil is it? Sand, clay, silt, or etc. I don't know what etc. is. A blend of those, plus some loess material and some organics. And at some moment in time, we would have a moisture profile in the soil. So this diagram here on the left, which is taken from Chow, Mabit, and Mays, the vertical axis moving downward is the depth axis. So as we go from this point 0 and move down the axis, we're going deeper and deeper into the soil. And these distances are maybe a couple meters. The surface depicted here graphically also serves as a moisture content axis. So here the moisture content at the 0 line would be considered 0, and then we get up to some place where it's saturated, which means there's no more room in the soil profile for moisture at that depth. So here's a diagram of a soil moisture profile under the conditions that the surface has received enough water. So imagine, if you will, a slight ponding right on the surface. Like when you pour water into a potted plant, the water, given a choice of going into the soil or spilling all over the table, just spills all over the table. Well, the moment that water forms a small pond, it's saturated at that location because there's no room for any more water at some depth. So here we have this, in the profiles we're moving down, very high moisture content, perhaps as much as the soil can possibly hold. And that would be called the saturation zone. And as we're moving down further, the moisture content as a function of position starts to decrease. And in this particular diagram, they call this section here a transmission zone. And we get to a point where the soil moisture starts to drop considerably over a short vertical distance. That knee, if you will, is called a wetting front. And our infiltration models often assume that below the wetting front, the soil is dry, and that's the terminology used, and above the wetting front, the soil is at field saturation. That's not realistic from a soil scientist perspective, but it's an awful useful conceptual model. On the right is some water content versus depth curves for some soil, and the behavior of the curves, it says it's calculated, so I imagine this is coming out of a soil science model. And it's showing what the moisture content is as a function of depth at different times. And up here at the top, you can imagine that there is a small pond of water whose depth is constantly maintained, just a couple of centimeters. So we have constant head at the top. And as water soaks into the soil, additional makeup water is added to that puddle, so the puddle never changes its depth. Under those conditions, in this particular soil, at about 1 hour, the wetting front, if you will, is 25 centimeters deep. At 6 times 4, at almost 4 hours, we've gone from 25 to 50 centimeters, and 500 minutes. At 10 hours, we're at 75 centimeters. So even though at the surface the water supply is constant, as it moves deeper into the soil, it takes longer and longer to get deeper and maintain these high levels of saturation behind it. There's some sort of nonlinear behavior there. It is nonlinear. This integral here, if you imagine at the surface, so here's our inflow in red, and do I have, I don't think I'm going to risk trying to do text. Yeah. Okay, so let me go back to my pen. We would have infiltration rate, and that is this script F, which is over here in the equation. If we keep track of the rate and multiply by how much time occurs, we get an infiltration volume, so that script F times some time equals the volume infiltrated. And in this particular case, they're using the symbol cap F for that. So the infiltration rate is dependent on where the wetting front is at any moment in time. And so the total volume that has infiltrated as a function of time is the integral from 0 to that time of the infiltration rate d tau, because the infiltration rate is going to change with time. We'll see later on why that's so, but in words right now, if you imagine that there's, let's go ahead and try a new color, blue. Okay, so if you imagine that we have a water surface up here of some non-zero depth, it has a depth of cap H, so that's the head at the top. If the wetting front's right there, the water pressure at that point is going to be 0 gauge, at 0 atmospheric. And if we consider everything behind it as wet, we can apply Darcy's law at the soil-water interface and the wetting front. The head at this end is cap H. The head at this end is going to be 0 minus Z. So Darcy's law says that infiltration is equal to Q equals K, cap H. It's going to be minus a minus Z, so it'll be plus Z. And then Darcy's law is it has a gradient, so it's the change in head over the distance, and the distance we've traveled is Z. You can see that when Z is small, the infiltration rate is, when Z is small, the top term is essentially negligible, and it's K times H. As Z gets big, the infiltration rate approaches a constant value of K. So the Q is a function of time, that time being determined by the position of the wetting front. These ideas are used to explain a couple of types of overland flow processes. So there's one concept called the infiltration excess concept, or frequently called Hortonian overland flow. And in Hortonian overland flow, the thinking is that the precipitation see, did it keep my pen color? Oh, it did. Cool. The thinking is that the precipitation rate is bigger than the infiltration rate. When that occurs, the precipitation partitions into the overland flow and the infiltration part. And that certainly is a usable mental model, although it may not reflect the actual physics that's going on. Nevertheless, it's a useful tool. So the infiltration excess is a pretty common concept that's implicitly employed in many of our computational approaches to explaining runoff. So this figure is taken from Broussard's text, and in the diagram, the precipitation rate P is exceeding the infiltration capacity, the ability of water to infiltrate. So what's left over becomes overland flow, makes its way off to that stream. Here's directly from Broussard's book. It's worth reading, so I'll read this to you. Same diagram on the right. And in his text, he writes, this type of flow, so referring to Hortonian, occurs when the rainfall rate is larger than the infiltration capacity, so that there is an excess which runs off over the surface. Although this flow generation concept is associated with the name of Horton, 1933, so that was Horton the who saw an elephant. It goes back much earlier. It was already the basis of the well-known rational method introduced almost 2 centuries ago by Mulvaney, and the various runoff routing procedures later on derived by Hawken and Ross and others. So see also Dooge 5773. So Dooge 1973 is a copy of that's on the server. It's also implicit in the unit hydrograph as originally proposed by Sherman in 32. In these and other early studies concerned with maximal rates of runoff in problems of flooding and erosion, it was assumed that the infiltration rate is smaller than the precipitation rate over the entire catchment. In the rational method, for instance, the infiltration is taken as a fraction of the precipitation, whereas in the unit hydrograph approach and in Horton's work, the infiltration capacity, or a related index, is subtracted from the precipitation. Thus, it was assumed that the infiltrated water is lost and that virtually all storm flow results from the overland flow of the precipitation excess. Now, here's the important part. In the prediction of extreme flows for design purposes in disaster situations, this assumption of overland flow was not unreasonable. That's his kindest way of saying, even though all these assumptions kind of don't match the physics, it was sure a useful tool. And it is useful. So I would advocate that this is a mental model to become reasonably comfortable with. If your goal is hydrologic science, it's probably not a correct model. If your goal is hydrologic engineering, it's a useful model. But the key is Hortonian excess. The infiltration has the concept of lost water. And the usual representation of Hortonian flow is Horton's model, which looks like the equation that's on the screen right now. If you look in Chow-Mavet and Mays on pages 108 to 110, this particular model is described in some detail. So the rate equation is shown here. I'm using lowercase q to represent an infiltration rate, inches per hour, millimeters per hour. That has a rate type unit. and it's equal to script F sub C, which represents the asymptotic value of infiltration. And by asymptotic, if you recall the diagram where I was showing Darcy's law, that would be where the wetting front is pretty deep, so that the infiltration rate is essentially equal to the saturated hydraulic conductivity, plus an initial value, F sub 0 minus F sub C multiplied by e to the minus kt, where k is a parameter of reciprocal time, and it represents how quickly the initial infiltration decays to the asymptotic value. So if k is a small number, then that decay rate takes a very long time. If k is larger, it's steep like here. If it's real large, it will almost be straight down and straight to the saturated conductivity. So the integral, the f of t, integral of 0 to time of q of tau d tau, represents this green area where time is on the horizontal axis, infiltration rate is on the vertical axis, and as time progresses, if you keep track of the area under the curve, you're getting infiltration volume. So this would be a useful model if F sub 0 were somehow predictable from soil properties. F sub C is predictable in the sense that it arguably would be the saturated hydraulic conductivity of an area, or at least an average value of that. So F sub C, I stipulate one could make reasonable estimates of that, but the initial rate is somewhat harder to come about. So the usual dogma on this particular model, Horton's model, is that the F sub C and F sub 0 have to be locally calibrated before use. That's kind of the consulting engineer's cop-out for let's go ahead and make some measurements to generate billable hours. A second approach to overland flow is called the saturation excess approach. And this one is associated with another hydrologist named Dunn. I think I have it spelled right. I'm not sure I can pronounce it right. So it's called, if you come across the words Dunn overland flow, you're not going to come across it in anything recent. I mean, this is knowledge that's lost to time. Anything from the 2010s onward is going to be all in computer programs. But if you come across terminology Dunn overland flow, it usually means a saturation excess concept. And in the saturation excess concept, we start with our watershed looking something like figure A here. And there's a water table here in communication with our stream. So ultimately the overland flow is getting to the stream. It becomes stream flow. That's still part of the runoff process. So we're interested in the conversion of rainfall into runoff in channelized portions. So the water table is beneath the ground surface. Everything's dry, so this water table is slowly changing slope as it's feeding water to the stream. Then it rains. So here's our precipitation. And as it rains, that precipitation infiltrates. Possibly all of it, in fact. And in doing so, it starts to recharge the portion of soil between the land surface and the water table. In doing that, the water table starts to rise, move towards the land surface. At some point here, the water table has become coincident with the land surface. So any precipitation in this region is immediately manifest as overland flow to the stream. And here the water table is still rising, so this overland flow component will start to move upslope away from the stream as more and more contributing area directly contributes to overland flow to the watershed. There's been a fair amount of research over the last 50 years using simple and exotic techniques, isotope analysis and tracer analysis, that make a convincing argument that the saturation excess concept is pretty common throughout the world, and is ultimately a better explanation of the overland flow contribution towards runoff production. Nevertheless, the other model, the infiltration excess, is a workable tool for engineering kind of hydrology questions. So it sort of doesn't matter which one, except that in the case of the saturation excess, we have to know how much water is likely to be stored before runoff occurs, and presumably we'd have to know where the water table is. It's a greater burden of data understanding or approximation to use saturation excess. Most of our modern computational hydrology tools have some ability to incorporate a saturation excess approach, but usually we apply them with infiltration excess because it's fundamentally easier to set up these systems. And then when we calibrate, we sometimes come up with goofy numbers. One explanation for that is that to make the model fit observations, we're modeling processes that are incorrect. It doesn't mean the model is useless. Here's a plan view of a catchment system illustrating the idea of saturation excess. So in picture A, everything's dry, and then by picture B, it starts to rain. So as the rain collects on the watershed, it all soaks into the ground, except in these locations that are very close to the stream. And what happens there is the water table rises quite rapidly up to the surface, so everything in the dashed area is now contributing to runoff at the outlet. And then as time progresses, that zone moves outward from the stream. And as I said earlier, there's been a fair amount of studies throughout the world that that support this story right here, which has some important implications for engineering and general civilization design. If you want to locate hazardous materials storage locations, and you want it to be there after rainfall, there's some evidence provided by a story like this that an area here that's pretty far away from the identifiable stream has somewhat of an added measure of safety because there'll be no direct runoff from the area. So as long as you can protect the material so it doesn't soak into the ground, you are also protecting your stream. That would be a difficult argument to make, but there's evidence here in these diagrams. So again, I'll read to you from the book because I think it's useful. So we're now talking about saturation excess. This type of surface runoff occurs over land surfaces that are saturated by emerging subsurface outflow. Here's that subsurface flow term again. From below and from perched water tables. That's pretty terrible English grammar there. Regardless of the intensity of rainfall. It is a rapid and almost immediate transport mechanism to the stream channel for the seepage outflow water and for the rainfall falling on such areas. It usually takes place in conjunction with subsurface flow to the channel, but the relative magnitudes of surface and subsurface flows into the channel depend largely on the nature of the catchment and the precipitation. It is most often observed over limited areas in the immediate vicinity of the river channel where downslope subsurface flows emerge, and in wetlands where the water table can rise rapidly to the surface. But it can also occur higher up in slope hollows, I believe that's pronounced holler, higher up in slope hollers, where elevation contours display strong curvature, thus forcing convergence of the flow paths. So that translates to it in regions of very steep topography. The saturation excess is quite likely. Outside of these saturated areas, all the precipitation and other input can generally enter the soil surface. If in your readings you come across the idea of partial area contribution, that concept and saturation excess concept are entirely compatible. I would argue that they're explaining the same thing from a slightly different perspective. Now we'll look at the subsurface storm flow. And again, borrowing from Broussard's book, I've taken a different picture. I think this is out of his book, in fact. So here's a chunk of watershed. We have rainfall coming in, and it provides new water, so fresh from the sky. The oxygen isotope ratio is much different than the water that's been in storage. As it soaks into the ground, they're showing a large portion here as subsurface storm flow. That's what these arrows are. But a fraction of that makes its way downward into the soil through, it's called vertical bypassing here. I'll show some photographs of evidence of macropores that would cause very rapid vertical transport of flow. It displaces water that's been in storage, and here generally they're showing the old water's coming out deeper. But it's quite possible the old water can come out fairly shallow, and we're getting out over here into a stream area. You sort of ignore the different geology indicated in this diagram. And as you come across these terms, saturated pipe flow, don't misinterpret it. There are no pipes, if you will, underground, at least not pipes that have been installed by human beings. But these are portions of the subsurface flow regime where water moves considerably faster than it does in regular porous medium flow. That's called piping. So in many catchments under natural conditions, infiltration is never exceeded, meaning it never rains hard enough. And the precipitation and other input readily enter into the ground surface, and thus the subsequent flow to the stream channel takes place below the surface, presumably through the soil mantle of the catchment. Loudermilk and Hirsch appear to have been among the first to propose subsurface flow as the main stream flow generation in forested hill slopes. It was later confirmed in several experimental investigations that subsurface flow can even be the only mechanism under certain conditions. And in this diagram, it's trying to convey the picture here. So here's our rainfall. There's infiltration, and there's a portion of flow to the stream that are these dashed arrows. That's the subsurface storm flow, or the rapid subsurface storm flow. And then there's solid arrows, which represent water that was already there that is displaced by the new incoming water. So generating runoff is a pretty complex process, and infiltration itself is a complex process. And that's what these few presentation slides are trying to convey. There's a lot of complexity involved. We'll have to simplify it for our computational needs in most cases. So nice segue. Scale is the appropriate criterion to classify the different methodologies. So there's two main kinds of approaches to classifying both infiltration and the runoff generation process. One is distributed models, also called runoff routing models, and these are at fairly small computation scales relative to the size of the catchment. So say the catchment is a couple of square miles in size, or even the size of that placid watershed that you analyzed in exercise set 1, which was several thousand acres. And let's suppose we modeled everything on a 1-acre grid. That would be a distributed model. We would explain the behavior on each acre, and then we would route surface flow from one grid cell to the next, ultimately to the outlet. An alternative to that is called lumped model, where we treat the entire catchment as the computational scale. If you've had undergraduate hydrology classes, the unit hydrograph method and the rational method that you were probably exposed to are examples of lumped models. Although they both can be cast in a distributed modeling context. So yeah, I think this distinction is somewhat artificial, but it is realistic. The importance of scale, in one sense, justifies efforts at delineation of knowing where the watershed is and is not, especially if we're going to consider saturation excess conditions, because at that point we very much have to have an accurate representation of the watershed area. Some distributed models are collections of lumped models. In fact, I would argue that most are, that are connected by hydraulic mechanisms. So the infiltration processes, whether it's lumped or distributed, are going to be important. Whether we choose them as a loss or if we're going to take our infiltrated water, add it to a shallow groundwater component, and route that to the outlet is an important decision to make. In all cases, it's going to be driven by our choice or availability of loss models. So in considering loss models, you have to examine the tools that you have. Are you making this yourself? I call it a homebrew. Are we using HEC-HMS, SWIM, something else? The tools will to some extent dictate how you will have to conceptualize the loss for a particular case. And then the second thing is, what are we asking of the model? The argument being, maybe if we're attempting to do hydrology for the sake of how big a culvert has to be, we could use a very simplified loss model, something like the infiltration excess approach, and that would produce adequate results for the purpose of making a culvert the correct size. If we're going deeper into that, to perhaps a water quality aspect or a longer-term simulation approach, we might have to use a more complicated model. So let's look at a few of the loss models. I'm going to look at 3 here in some detail, and I have them in parentheses. I've identified the 2 computer programs I selected for this class that contain the various models. So one of them is an NRCS curve number model, which is not really a loss model. It's actually a runoff generation model, but if you subtract the runoff signal from the rainfall signal, what's left over had to be lost. So I guess it is kind of a loss model. The second one is a green amped model, which is very similar to the infiltration excess approach with a Darcy law component to it. And then a third one, I call it initial abstraction constant loss. I think it goes by some other names. So the first 2 are in SWIM and HEC-HMS. The third one, initial abstraction constant loss, is in HEC-HMS only, and in SWIM you have to hack some input to do it, which is not hard, but it's not directly built into the program. Some other methods, one is called the exponential model, which is in HEC-HMS. The exponential model was essentially the Hortonian model that had the initial infiltration rate and the asymptotic rate. There's a technique called the phi index or proportional rainfall. In the past, I've used that extensively, and that simply says you take the incoming rainfall and you immediately remove a fraction of it from consideration as direct runoff, and then continue on with your runoff calculation, and that kind of doesn't fit anything. I guess it's a distributed abstraction approach. It's useful. It produces useful results, but not much engineering or watershed science involved. There's a soil moisture accounting model, which is part of HEC-HMS, and that's fairly elaborate. It's very much a combination of infiltration excess and saturation excess. And because you're accounting for moisture in the soil, it gives you the ability to keep track of that moving water table, in a sense, and determine what flows get to your receiving conduits. And then a deficit constant model is another HEC-HMS implementation. So there's quite a few choices one can make when doing the computational hydrology aspect of surface water hydrology. And generally the questions that you're asking of the model will guide your decision. All other things being equal, the simplest is going to be probably the best, because you'll be able to obtain the data or explain the results better. So we'll start with the NRCS model. It's described in detail in Chow, Maybit, and Mays on pages 110 through 122. It's also pretty much, if you type NRCS curve number method into a Google search, you'll probably get several 100,000 explanations of it. They're all going to be fairly similar, and if this one doesn't make any sense to you and Chow, Maybit, and Mays doesn't, you can find something on the internet that will. Since they're all tracing back to the same original source, your personal preference in that, whichever makes the best sense to you, is the one to use. So let's look at this diagram. So I have precipitation rate on the vertical axis and time on the left-right axis. Actually, let me get my pen out. Now, I just realized I had a pen. Let's see. I usually draw rainfall as, red. So here's my, I'm going to draw it as a set of blocks. So there's 1, 2, oh, my hands aren't really this shaky. I guess I shouldn't have had all that cough syrup this morning. Okay, that was a joke from Stripes. I didn't really have any cough syrup today. Okay, so there's our 1, 2, 3, 4. There's 5 rainfall blocks, if you will. And so, there's a rainfall depth. And there's a, see, what do I use? I need a color for loss. Okay, I use blue for runoff. Gray, that's a good loss color. The initial abstraction concept, I sub A, is a concept that says when rain begins, a certain portion of it is completely removed from the outflow signal, and then, that's water that's going into storage, evaporating, getting stuck on tree leaves. So in the SCS model, they have a portion called initial abstraction. And in this diagram, it's that gray portion. So that first pulse of rainfall, if you will, is becoming unavailable for runoff. Then once the initial abstraction portion is satisfied, infiltration begins, and that's called the continuing abstraction component. And in the SCS method, if the rainfall is greater than the abstraction component, what's left is the excess. So this blue area up here for that rainfall pulse is excess, and this gray area down here for that pulse is added to our loss collection. Then as time goes on, that abstraction rate decreases because we're filling up the various stores, if you will, or we're approaching the asymptotic infiltration capability. And so there's our next loss component, our next one, and so on. And you notice this kind of levels off to an asymptotic value. So the loss as a rate never goes to zero, but it gets small. And up here, these blue are the excess component. And so that's shown here as P sub E, the excess rain. And that terminology is important because the runoff we observe by conceptual definition equals the excess rain. Excess means rainfall that's available to become the runoff, and everything else is accounted for somehow else. So the shape of this curve and the amounts of the blue that's left are related to a property called a curve number. And it's done so with this particular formula. It says that rainfall excess is equal to the raw rain, or the total rainfall coming in, minus the initial abstraction, quantity squared, divided by the raw rain minus the initial abstraction, plus the watershed retention. Think of that as a storage term. Now, whether it's retained on the surface or in the subsurface is not, that is not distinctly quantified in the SCS method. It's just retained on the watershed. Dude, I'm making a video. Don't. Oh, gosh, you're huge. So this term S is specific retention. Now, historically, the SCS decided that the usual abstraction is 20% of the watershed retention. And that's not by any first principle things. They studied various research watersheds and decided that was a pretty good average. And so over time, that's become almost dogma in the method. Although there's nothing that would preclude you from making a different fractionation. And so we make that substitution, 0.2s for the I sub A term, and now we have the excess precipitation is raw rain minus 2/10 of retention, quantity squared, over raw rain plus 8/10 of retention. So we've mapped initial abstraction into another concept, watershed retention, and then the retention is related to a quantity called the curve number, according to this formula. So the retention is 1,000 divided by curve number minus 10. And that substitution is made, and now you have excess rainfall. Excess rainfall is correlated to curve number. And so the curve numbers are tabulated for various soil properties and land use properties. There's 4 different types of hydrologic soil conditions, A, B, C, or D. And so that was based on the Jackson 6, which was the original band. And ultimately, they went down to Jackson 5, and it was ABC, which is easy as 1, 2, 3. And land use is assign a curve number between 10 and 100. If we looked at a curve number of 100, 1,000 over 100 is 10. Minus 10 would be equivalent to a retention of 0. So curve number of 100 is a condition that completely converts raw rainfall into runoff. Arguably, a parking lot could do that, although by practice we usually assign parking lot curve numbers of 98, and that's just a decision that's made because over short time you don't get 100% out of a watershed. But you ran the thing for 2 weeks of rainfall and 1 inch an hour for 2 weeks, that'd be a huge amount of rain. At some point what comes in is going out. So high curve numbers are perfect converters of rainfall to runoff. Low curve numbers, there's a substantial amount of watershed retention, and then what's left is runoff. Oh, I just said that. Just as a reminder, curve numbers is not percent impervious, although sometimes it seems like the numerical values of those two are pretty close. And curve numbers is not percent of precipitation. So curve number 100 is the only one that is that if you have curve number 100, 100% of precipitation will become runoff. But if you have a curve number less than 100, you can't make that blanket statement. And I hope my next slide is a picture of curve number method. We're getting there. So the NRCS curve number method uses a separate computation of impervious cover, and then that's applied to pre-development land use or composite curve numbers. Compositing is described in many places. The Hydraulic Design Manual for Texas is an example of one. There's some on the NRCS website. Good. I knew I would have some tables. So let's look at an example table for rural conditions. So the curve number tables, like this one, they're pages and pages. And this particular table is taken from NEH 630, which means the National Engineering Handbook. So the USDA publishes, it's online now, the National Engineering Handbook, section 630, which is hydrology, chapter 9, which is curve number method. So there's pages of tables like this in this document. And so it starts with a descriptive process. So the type of soil cover, so row crops, and there's probably pages for grassland and harvested forest and so on. And then the cover treatment, whether it's bare soil or residue, straight row, contour plowing. And then there's a hydrologic condition. You have to read the footnote for what poor is or good. Good generally means that it's a well-drained soil, and poor means it's a poorly drained soil. And then there's hydrologic soil groups, and those themselves are defined in the engineering handbook. And finally, we have curve numbers for these different conditions. So we'll see, let's look for bare soil fallow, hydrologic soil group A, which would be a relatively poor soil, maybe high in clay and silt, has curve number 77. If we grade over to hydrologic soil group D, which is going to be a well-drained soil, sand, clay, silt, mostly sand, has a curve number of 94. You'll notice that the curve numbers are represented as whole numbers. There's no fractional component. There's not like a 91.2. And when you are compositing or building a composite curve number for a study, you don't want to report fractional curve numbers, because although you can do the arithmetic and you get a fractional number, you get 92.3. That doesn't make a lot of sense. The actual impact of a 92.3 versus a 93 or a 92 is generally negligible. You can't even see it in the computed output. So the usual guidance is a report to the nearest whole curve number. As we're moving on, there's also curve numbers for urban areas, and they're not too interesting. So if it's a paved area, it doesn't matter what the underlying soil is. The curve number is 98. And then here's some open spaces, lawns, parks, golf courses, cemeteries. I'm surprised the cemetery is that high, because those are going to have a bunch of low permeability inclusions, about 6 feet beneath the soil surface. And then different conditions. And so depending on the soil group, it's grading from 68 to almost 90. So one of the important things for the curve number method when it's applied for infiltration is making a defendable decision on what the hydrologic soil group is. And then once that's done, that helps choose a column in this table. Here's the composite formula for use in urban areas. So you have the curve number of the pre-development conditions or the underlying soil, and then you take the percent impervious, divide by 100, multiply by 98 minus the curve number of the pervious conditions, and the result becomes the composite curve number. And then runoff is generated in a formula like this. So once you have the curve number, the specific retention is fairly easy to compute. And I'm showing here a slightly different way, slightly different representation of the same equation that I think is easier to program. And then that S is put into the upper equation, raw rain is applied, and then what's left is the runoff generated. Where it gets tricky is if you're doing it for subsequent times, and I'll leave that to you to do some reading on that. My 2 cats have just come and joined us. One of them is soaking wet. I don't know why, but he's sharing the wetness on me. I hope that's just ordinary wetness. Another way of representing the curve number method is with this chart. This is a graphical solution of that equation. So if you know the curve number and you know the rainfall, you would read up from your rainfall rate to your particular curve number to get a direct runoff depth. These are all in watershed inches. What's interesting on this curve, and it's not in any of the SCS documents per se, but if you were to incorporate the third variable of time, what these lines represent are trajectories. So and let's pick a curve number. I'm going to use 75 as a for example. So at the beginning of rainfall event, a watershed that has an average curve number of 75, for the first inch of rainfall, doesn't produce very much runoff. Okay, and we use the pen because it doesn't want to work right. 75. So the first inch of rainfall doesn't produce very much runoff. Then as time progresses, let's say we get the third inch of rain, by then we would expect to have seen 1 inch of runoff. It looks like I'm on, we get to 5 inches of rain, 2.5 inches of runoff. Again, time is progressing. We get to 7 inches of rain, we have about 4 inches of runoff. And as we get way out here, 11 inches of rain, we've got 8 inches of runoff. Now what's important to observe is to look at the slopes. And at this far end, the slope of these two curves is the same. And so what this is telling me, if you look at 2 points in time on this trajectory, here we have 1 inch of rain produced 1 inch of runoff. So later in time, when the watershed's fully saturated and there's no place else to retain water, what comes in goes out. And so from that respect, curve number method has a certain philosophical attractiveness, if you will. But it may take weeks to produce 10 inches of rainfall depths, which kind of blows it out of the water for an event approach. There's detailed explanation in chapters 9 and 10 of NEH 630, and the highway hydrology textbook, which is on our server, also has a good explanation. And most hydrology textbooks, hydraulic design manual, circuit current, doesn't have to be 2009. And the advantages of it are it's a simple documented approach. It's widely used and established across the United States. It probably is used in other countries. Oh, I just figured out where the water came from. The cat just stuck his paw in my drinking water. No more drinking water today. The disadvantages are the losses approach zero at the latter parts of a storm, which is probably not correct. And there's the same loss for a given rainfall regardless of duration. So however long it took us to follow that trajectory, the loss is the same. And that is not accurate. Let's go take a reading on infiltration notes. So there's Horton's infiltration model, and there's some discussion there. Here's the phi index model, which I don't have in the slides. Gradient, which we'll get to shortly, and curve number method. So we've just gone through this, and here's some of my thoughts on the curve number approach. It's in wide use, and hence there's justification for it as a loss model. It's well documented, but in the original documentation, there's not much explanation of how it was originally developed. Chapter 10 of the NEH goes through the derivation of a curve number procedure. I have a physical plausibility argument of the curve number method that I'll read to you here relatively quickly. If we assume a watershed can be represented as a linear reservoir where discharge is proportional to accumulated storage, and then using the curve number names and definition, we can construct a discharge function that's decaying exponential. And the decay rate contains the same information as the curve number. So there's our linear reservoir model, and if we consider accumulated storage depth on the watershed area, there's a portion that's assigned to initial abstraction, there's a portion that's assigned to continuing abstraction or the specific retention, and then there's a discharge portion, which is the discharge rate, lowercase q, times the watershed area. And then there's an input portion, which I'm showing here as I, which is the rainfall. We do a little calculus, and the change in storage is inflow minus outflow, if we divide out by the area. And if we assume a linear response, we can state that the outflow rate is a constant times the accumulated storage. And from that, we can further stipulate that the outflow rate related to inflow rainfall is shown here, where it's 1 minus e to the minus t over alpha. And in this case, time begins once the initial abstraction is satisfied. Now, if we use the definitions of total depth and excess depth from the NRCS documents, we can integrate that term, and there's a result of the integration. We can assign values that total precipitation is the actual input plus whatever's stored in initial abstraction plus whatever's stored on the watershed retention. And then when we start plotting the PE as a function of time, we get curves that look exactly like they do in the NRCS method. And we see that the charts contain the same curves. In this case, what's changing is the alpha term, and in my opinion, the alpha term can be related as 100 minus curve number over 10. So the first curve is for curve number 90, the second one is for a curve number of 60. I times alpha is the specific retention, so that's a very similar concept as in the NRCS method. And lastly, a runoff starts in the time domain. So the curve number method has some explainable physics in it. So we're running out of time, so let me return and finish up the presentation. I didn't think it would take that long. The curve number is described in HMS user manual on page 137. We'll see that when we get to using the HMS tool. Second loss model is a green amp, and I'm going to have to go through this fast, which is unfortunate because this is the a loss model that explicitly considers soil properties. It's based on constant head or constant flux into a porous medium. It assumes the soil is acting like a permeameter. It uses Darcy's law, adjusted for soil suction, has 4 parameters: initial and saturated water content, soil suction, and saturated hydraulic conductivity. And in that green amp model, the real moisture profile on the left is replaced with an idealized moisture profile shown here. So there's a wetted zone, and then beneath the wetting front is, if you will, a dry zone. And instead of this curve profile, there's a step change at the wetting front. Here's a cartoon of that. The leftmost picture is at time 0, nothing's happened. The middle drawing is time 1. It's started to rain, and water's collected in our soil, and it has a non-zero depth of capital H. And right here is where infiltration occurs, at the water-soil interface. And then it soaks into the ground and starts to produce this column of wet soil. And the wetting and drying front are shown here, and they're moving downward. And they're moving downward in proportion to how much is infiltrated. So at a very short time, it hasn't moved downward very much. As time gets longer, it gets deeper and deeper. So the estimation of parameters is fairly straightforward. Initial water content, a value you can use is the wilting point in your region. That's usually findable, may not be easy to find, but you can get wilting points for soils in a particular area. The saturated water content, porosity is a good approximation. The saturated hydraulic conductivity, 2 approaches. You can make actual infiltrometer measurements, or you can use the web soil survey because it reports a permeability for your area of interest. Soil suction, you're kind of on your own there. You can use the textural description or hanging column experiments. I would probably use my web soil survey to get an idea of what if they report porosity, you can make a pretty good estimate of soil suction from the porosity and the soil materials. So if you know it's clay, suction's a couple meters. If you know it's sand, maybe suction's maybe 30 centimeters at best. And you can ignore suction. You can set it to 0 and still get meaningful results. And then in some places there's local guidance. For example, Harris County has green amp parameter values. The advantages of it are it's a solution to a simplified soil moisture equation. Parameters can be estimated by measurement or description. Disadvantages is that estimates are non-trivial, and it's often more complex than the rest of the model. And the explanation of it is on page 133 of HEC-HMS. There's also an explanation of it in SWIM. The last one is the initial abstraction constant loss. This is pretty easy to describe. It assumes an initial abstraction, just like NRCS, and then a constant loss rate expressed as a rate. So that constant loss rate might be ½ inch an hour. And then there's no recovery of initial capacity when there's no precipitation. So here's the model. Precipitation comes in. There's an excess once the initial abstraction has been satisfied and the loss rate is satisfied. Some typical values are shown here for sand, initial abstraction up to 1½ inches. Constant loss rate, 0.3 of an inch per hour. And then once you have the two parameters, the model's very easy to apply. If the rainfall rate has not yet satisfied the initial abstraction depth, then all the rain is assigned to that depth. And then once that's happened, if the rainfall rate is less than the loss rate, there's no excess for that time block. If the rainfall rate is bigger than the loss rate, there is excess. And then proceed accordingly. This is a simple model to set up, and there's a document on the server, 4193-7, which discusses application of the model. In many cases, it's considered too simplified, but it is a good starting point. In the HMS user manual, this is what they call the initial and constant loss model. Some of the other loss models are listed here in this slide, and I'll let you read those on your own. They're documented in many places. The exponential model is the same as the Horton model, and that's it for today's presentation. I'm sorry, I thought I would have gone faster. Are there any questions? All right, well, I will release you back to your day, and I hope that you have a good afternoon. And I'll stall just a little bit longer to be sure anyone that wants to ask a question has a chance to. I'll get this video posted. It's taken me a long time to upload stuff, so I can get them rendered in no time at all. But the internet's running really slow for me right now. So I expect to have them posted, well, surely by tonight, because it's been taking about 6 hours. So you'll be getting an email from me for tomorrow's invitation. I'll include the link to today's lesson. I may even take some time and do some supplementary video on some of the written notes that I wasn't able to get to today. So thank you very much for your attention. I think there's an assignment due today. I think it's due this evening, but again, I don't know. The server time is 3 hours different than local time. So the server's running 3 hours early, which is odd because it should be 7 hours early. So noon time local is the same as 9 o'clock on the server. So keep that in mind as you're getting close to the due time. Though I don't think that's a problem for anyone. Thank you very much. Have a great afternoon. I'll see you tomorrow. Bye-bye.